Welcome back to Science Fantastic with Professor Michio Kaku. We profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And this hour, once again, it's open mic. That's right, it's open mic on Science Fantastic. Okay, let's move on now and take the first listener phone call.
Hello, my name is Jacob Hutchinson. My question for you is, I've read that if you fall into a black hole, you see the whole timeline of the universe flash before your eyes. Does that depend on the mass of you in a black hole, or is that a universal truth? Thank you.
Well, you ask a very interesting question, because many people have wondered what happens when you actually fall into a black hole. What do you see? What sensations do you have as you fall into a black hole? Well, with our telescopes, we can actually see stars, star clusters falling into a black hole. The black hole basically has lunch. Now, realize that light, ancient light, can be trapped orbiting around the black hole. And so as you enter a black hole, you'll encounter ancient light that has been trapped, caught, whipping around, orbiting around the black hole. So in some sense, when you fall into a black hole, you see the history of the black hole. When it was created, how it was formed. It's sort of like some people say when you have a near-death experience, you see your life displayed in front of you just as you are about to die. Well, in some sense, the same thing happens with a black hole, because a black hole has captured ancient light going all the way back to its original formation, and you see this when you go toward the black hole. Now, it's not very pleasant falling into a black hole. First of all, tidal forces, gravitational forces tugging on your toes, is different than the gravity forces tugging on your head, so you get stretched as a consequence, and that's called spaghettification. You literally become a noodle as you head toward a black hole, as tidal forces stretch your body until eventually your body disintegrates into atoms, and then the atoms themselves get ripped apart by gravity. Gravity rips apart the electrons from the protons, and so you are basically a bunch of gas molecules and subatomic particles as you enter the black hole. Now, if that isn't enough, time also slows down as you enter the black hole. Now, if you watch this suicide as you head toward a black hole, if you see this from a distance, so let's say you're in a rocket ship far, far away, watching this sad episode with a telescope, what do you see? Time slows down from your point of view. You see that it takes hundreds, thousands of years for that person to fall into a black hole, because the light from the black hole is what is called blue shifted. Frequencies change and time slows down. Now, if you are the unfortunate person to actually fall into the black hole, then it would only take a few seconds for you to fall into a black hole, depending upon where you started from. So, from your point of view, you've already vanished into the black hole and perhaps are dead. But to someone far away, watching this whole spectacle from a safe distance, you would see the person frozen in time, because time slows down as you head toward a black hole. In fact, I once read a science fiction story where the bad guy, at the end of the novel, falls into a black hole and he screams for 1,000 years. Okay, well, let's move on now and take the next listener phone call.
San Jose, California, Albert. 2001, A Space Odyssey. The movie, I'm sure you're well familiar with it. The computer HAL 9000. Do you think today they can make a machine just like HAL? And as far as consciousness that you've always mentioned about robotics and machinery, I don't think it would be self-aware. It merely mimics the human mind, but at a phenomenal rate of speed. That's why it outwitted the crew of Discovery 1. I've done a lot of research on that. So what's your opinion? Is there a HAL 9000 today? Certainly not from Urbana, Illinois. And I just wanted your opinion. By the way, he was a Capricorn, too, by the way, if that helped anyone out. Thank you, Doctor.
Okay, well, first of all, yes, I've seen most of the great science fiction movies. I love going to the movies. When I was a kid, I would thrill at all the exploits of astronauts going into outer space. Today, however, I cringe a bit because being a professional physicist, I can see all the mistakes and errors that are made in the movie. However, you have to suspend your beliefs a little bit and just enjoy the show. I enjoy watching science fiction movies. And 2001, I think, is one of the most realistic movies, but I think they got the date wrong. Instead of being 2001, it should have been 2100. That is, I think he was off by about 100 years. 100 years from now, we may have regular manned journeys out to Jupiter and beyond. And perhaps by the end of this century, we'll have robots that are every bit as intelligent as us, and we can have intelligent conversations. Now, today we have Alexa and things like that are called chatbots. That is, they can talk to you, they can answer simple questions, but you can't engage them in gossip, you can't talk shop with them, you can't treat them as a friend. And that's where robots have failed. Robots are very good at things that are repetitive, things that don't require imagination or creativity, but they fail in 3 or 4 big areas. Listen carefully, because these are the areas where there are going to be jobs in the future. I repeat, the jobs of the future will be areas where robots cannot fill. One is human interactions. So, for example, in a law firm, the paralegal may be replaced because the paralegal is basically a search engine looking through law books. But the lawyer, him or herself, has to engage the jury, has to understand ethics and morals of society, which constantly change, have to argue to a judge and a jury. And so human interaction is one thing where robots are very deficient in. And this means that those jobs that require those skills will be around for quite a while. Next is pattern recognition. For example, our most advanced robots cannot fix your toilet. Things that are non-repetitive and require semi-skills cannot be done by robots. Robots cannot pick up garbage. They cannot solve a crime like what policemen can do. They cannot build a house like a carpenter. And they cannot make a garden like a gardener. But things that are repetitive, that's where robots can excel. So pattern recognition is another area that robots do not do very well at all. And then there's common sense. We know that water is wet, not dry. We know that mothers are older than their daughters. But how do you know that? How do you know that strings can pull and strings cannot push? Well, that's common sense. Any idiot knows that, right? Well, yeah, any idiot except robots. Robots do not know that water is wet because they never encountered water and wetness. I mean, why can't water be dry? And mothers are older than their daughters? Well, according to Einstein, that's not necessarily true. But for the most part, mothers are older than their daughters, but robots don't know that. And so jobs involving common sense will also be off the table for quite a while. And then jobs that require imagination, originality, innovation. Those are jobs that robots cannot perform well at all. So intellectual capital is going to be the currency of the future, not commodity capital like agriculture, making metals and different kinds of commodities, but intellectual capital, the capital of the mind, making jokes, creating new scientific theories, becoming a teacher and a mentor. These are things that require human skills, and that's where robots are lacking. And maybe in 2100, that movie, 2001, will in fact become very close to reality. Okay, let's move on to the next listener phone call.
Hello, Doctor. My name is John Cloud, and I'm calling from Pasco, Washington. The call letters of the radio station is KONA AM 610. I am wondering about a product that has been around surfacing here in the United States called Tribotex. It's they say smart nanoparticles. It goes inside of a gas and diesel engine. I want to know how safe that is and if that's a gimmick or what. nanoparticles that say superlubricity. Could you please explain what that is? Thank you.
Well, there's a lot of hype around nanotechnology, which is the technology of individual atoms. And in the future, one day, perhaps we'll have atomic machines that are the size of atoms, atomic levers and gears and hammers, and that could create, of course, a new industrial revolution at the atomic scale. But where are we today with this technology? The promise is you could become a magician, like Harry Potter. You wave your magic wand and a rabbit comes out of your hat because you rearranged atom per atom the molecules in that hat. We are far away from the promise of nanotechnology. So where are we with nanotechnology? One is lubricants. That is layers of surface with, let's say, carbon and carbon composites and graphene that can form layers on materials to give them strength, to make them slippery. And so that's one area where there is an industrial application, is in micro lubrication. Also, graphene, I mentioned. Graphene is a single layer of carbon. And as a consequence, scientists have been able to make transistors out of a single carbon atom, which will eventually give us molecular transistors. I mean, think about that. Instead of those clumsy silicon transistors that you find on your PC or your cell phone, we'll have transistors the size of carbon atoms, and that could give us a new industrial revolution. Now, there is some controversy, as you pointed out, and that is safety. At the present time, the safety tests on many of these chemicals have not been thoroughly done. And so we assume, for the most part, that these industrial lubricants are not going to be harmful. But, hey, you never know. It's one of these things that still have to be tested. So for the chemical you mentioned, I'm not sure, I'm not familiar with that specific chemical, but you have to be careful because lubricants have been used, microlubricants made out of nanotechnology, but you have to worry about how safe they are and whether or not, for example, the FDA has given any guidelines. But this is a frontier area. Another area where nanoparticles are very useful is medicine. It turns out that you can create nanoparticles that home in on individual cancer cells, killing them one by one. That is astounding. And some people think that's the future of cancer research, knocking out cancer cells one by one. One way to do that is to modify your immune system. This is called immunotherapy, so that it recognizes cancer cells and kills them. Another is to artificially create nanoparticles, which also zoom in on cancer cells and knock them out one by one. All this, of course, is still at the cutting edge, but one day nanomedicine can really turn ordinary medicine upside down. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, once again, we're going to throw the lines open because it's open mic on Science Fantastic. Let's move on now to the next listener phone call.
Hi, I'm Andrew Rosick, calling from Richmond, Michigan, and I had a question for you about light waves, and I was wondering if a wave of light was a dimensionless phenomena or had dimensions that can be explained. Thanks, Barrett.
Well, you ask a very intriguing question that has dogged science for centuries. Light does seem to be different from other objects. For example, if you take an object and you boost it, you have to, kick it or put a rocket on it, and it takes time. It takes time for an object to build up speed, and it's a question of inertia. So objects have inertia or resistance to change. Light, on the other hand, you turn on the light switch and bingo! It immediately races at the speed of light. No warming up. no getting up to speed. It immediately goes at the speed of light. And so you say to yourself, well, light really is different from other kinds of matter. It's really quite different. And the reason is the mass of the light beam is zero. Not that it doesn't have zero dimension, it has zero mass. Therefore, it takes no effort to simply turn on a flashlight and boom, it goes to the speed of light. No warming up, no revving of your engines, none of that. Immediately it goes to the speed of light because the mass, the rest mass of light is zero. Now some people say, now wait a minute. Einstein said E equals mc squared. Energy is mass times c squared. M appears in that equation. So doesn't light have mass? And the answer is no. You see, E equals mc squared is actually a truncated equation. It's not the complete equation at all. The complete equation is quite different. And for light, it is energy is equal to momentum times the speed of light. And so momentum can even exist with zero mass. And so you see, the equations for light really are different from the equations for ordinary matter. But we know E equals mc squared. We don't know the equation for light because, unfortunately, they don't teach it in elementary school, even though they teach E equals mc squared. Now, does light have dimensions? And the answer is yes. In fact, it is a wave. You can graph it on a sheet of paper. In fact, it was James Clerk Maxwell, 150 years ago, who first discovered what light really is. If you get a magnetic field, for example, and you vibrate it, it creates an electric field. A vibrating electric field creates a magnetic field. That's how motors work. That's how your bicycle lamp works. Anytime something spins or moves, it creates an electric field and a magnetic field. Well, Maxwell then got a sheet of paper and drew this curve. You get a wave, one wave creating the next wave, creating the next wave. And then he asked the key question, a question which really changed human history. What happens if electricity turns into magnetism, turns into electricity, turns into magnetism, and it goes back and forth, and it creates a wave of electricity and magnetism. Well, that was actually figured out 150 years ago by the British physicist James Clerk Maxwell. We know about electric fields. For example, electric fields make your hair stand on end if you get charged up. It's the spark you feel by walking across the carpet. It's the electricity you get from the wall. And it's the electricity you get in a lightning bolt. All these are due to electric fields. Then we have magnetic fields, like the magnetic field of the Earth, which makes compass needles point in the direction of north. And then you have dynamos and motors. How do they work? Electric fields turn into magnetic fields, which turn into electric fields. So, Maxwell said, if I have an electric field, and it turns into a magnetic field, like a ping pong, it goes back and forth, it creates a wave. And then he said to himself, well, that's nice. If vibrating electric and magnetic fields create waves, then what is the velocity of this wave? Well, it's a very simple calculation. He calculated the speed of the wave, and then he practically fell off the floor. He made one of the greatest discoveries in the history of the human race. He discovered that the velocity of a wave created by electricity turning into magnetism, turning into electricity, the velocity of that wave is the speed of light. And then he said, I paraphrase, he said the most momentous words of the electric age. He said, this is light. Light is an electromagnetic field. It's a field created by electricity turning into magnetism, turning into electricity, vibrating back and forth like a ping pong ball, traveling at a velocity, and that velocity is the speed of light. And then Maxwell said, this is light. One of the greatest discoveries in the history of the human race. And then Einstein, a century later, actually about 40 years later, took these equations of Maxwell and finished it. Unfortunately, Maxwell died when he was 40-something years old, and he was not able to complete his theory. Einstein took Maxwell's theory and said, this is just the beginning. That is, if this is light, then let's calculate the speed of light as you go in any direction. And then Einstein realized that the light beam traveled at the speed of light no matter how you looked at it. And then he came up with the theory of relativity. And so what is light? Light is an electromagnetic field. Electric fields turning into magnetic fields, turning into electric fields, traveling at a velocity, the velocity of light itself. Okay, let's move on now to the next listener phone call.
Hi, my name is Shane Thompson. I'm listening to iHeartRadio, KFBX, Fairbanks, Alaska. I'm currently in Fountain Valley, California. My question for Michio Kaku is, what are your thoughts on the grand solar minimum? The way the sun seems to have an effect on our weather here on Earth and causing climate change. Thank you.
Okay, yes, if you take a look at the sun and graph the sun's output over a long period of time, you realize that it's not steady. You begin to realize that there are fluctuations in the sun. And, for example, years ago, the sun's intensity was different than it is today. And if you look at the history of stars in the heavens, there are so many stars in the heavens that you can see stars in any phase of their life, from birth to maturation to eventually they die or they undergo a supernova. You can see stars at any phase of their existence. And so with stars, we can then compare the life history of thousands of stars to the life history of the planet Earth. And you see that, yes, it turns out there are cycles, that there are areas where light can diminish or expand. However, I'm not so much worried about that. I'm worried about when the sun has a temper tantrum, that it erupts with the fury of a solar flare. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, if you want to be part of the March of Science, then give us a call at 612-564-8135. And remember, no question is too dumb, too stupid, or too dumb to put on national radio, because sometimes the dumbest questions are the most profound of all. They're the most revealing of the secrets of Mother Nature. And so give us a call at 612-564-8135. Before the break, we had a question about the sun. Yes, the sun does have cycles. Yes, the sun's intensity can increase or decrease. But does that cause global warming? No, it is not sufficient to influence the weather that much, especially because the weather has been changing over the last 100 years. And many of these cycles take place over a period of thousands of years. However, there's one kind of event that really, really does worry climatologists, and that is a gigantic solar flare like the Carrington event of 1859. It was a gigantic explosion on the sun as a solar flare went hurtling from the sun and hit the Earth, and it was seen by the astronomer Carrington. That's why it's called the Carrington event, and it influenced telegraph wires back in 1859. Now, we physicists today, knowing the intensity of what it takes to disturb telegraph wires, can then now extrapolate to what it would be like today if a Carrington event were to erupt today. And it's not going to be very pretty. Property damage will be on the order of $2 trillion. That's trillion with a T, not a B. It means that power plants would be short-circuited, satellites would be fried, telecommunications will be disrupted, the internet will go down, your power in your house would go out as the power supply is short-circuited, credit cards cannot be taken because, of course, everything's offline, and it means that refrigerators are all going to go on the blink because there's no power, which means food riots in the next few days. It's going to be a real mess. And so we physicists, knowing this, went to Congress and said we need a few $1 million in order to reinforce our satellites, reinforce our power plants, build redundant systems as a safety precaution. And all we get was snickers. Snickers from Congress. So much for alerting our wise lawmakers about a real potential catastrophe when the sun erupts in the fury of a gigantic coronal mass discharge like what we had before. Now, how often are they? We don't know. Perhaps on a scale of hundreds of years, we don't know. We've only had one, and working backwards, we've been able to work out the dynamics of that solar flare and exactly how intense was the electric field. For example, we know that as you travel north, you get the aurora borealis because of the solar wind which hits the North Pole. However, during the Carrington event of 1859, as far away as Cuba, they saw the Northern Lights. The Northern Lights not in Finland or Sweden. No, the Northern Lights in Cuba. That's how massive this solar flare was. And as I mentioned, we physicists can then reverse engineer that to calculate the intensity of that solar flare. And it was humongous. It was off scale, meaning that every few hundred years, a whopper is going to happen. And remember back in 1859, what did we have? Did we have television? Did we have the internet, iPods, iPads? No. We had Morse code and telegraph wires. That's all we had back in 1859. Think of what that would do today to our power plants, to the satellites, the internet, telecommunications, telephones. It would be a real mess. Okay, let's move on now to the next listener phone call.
Hi, Dr. Kaku. My name is Eddie. I live in Ogden, Utah. I just watch your show, or listen to it on YouTube, rather. I had a couple questions that maybe you could clarify. I think that your listeners would really be interested in is, can you explain what frame dragging is, as well as the tachyon antitelephone paradox? Thank you. Love your show.
Okay, frame dragging is a consequence of Einstein's theory of general relativity, where space and time have a life of their own. They are a fabric which can bend and stretch, and that gives us the appearance of gravity. So the pulling and tugging of gravity is actually the pulling and tugging and stretching of space. Now, as a black hole rotates, it's like molasses rotating, and if you are, let's say, a bug floating in molasses, you are dragged along with the molasses as it spins. That's called frame dragging. So frame dragging is when you have, for example, a black hole, and you're caught up in the wake of the spin, and you are then dragged along with the frame being space and time. So that's how that works. And we actually see frame dragging. This was, of course, a consequence of Einstein's theory of 1915, but we actually see evidence of this as we see entire star systems and gas clouds suck right into black holes as they have their lunch. And then tachyons. Well, first of all, let me explain what a tachyon is. A tachyon is a hypothetical particle that goes faster than the speed of light. And if it goes faster than the speed of light, then in some sense it gives you a form of time travel. That's why we physicists are very skeptical about the existence of tachyons. Of course, on Star Trek, tachyons are a preferred way of communicating because it would allow you to communicate faster than the speed of light. However, don't believe it. We have seen no evidence of tachyons. Maybe a tachyon destabilized the Big Bang at the beginning of time, but that's about it. So far, we see no evidence of tachyons. Well, unfortunately, that's it for Science Fantastic. Once again, join us every week as we explore the cutting edge of science on Science Fantastic. And give us a call. The hotline number is 612-564-8135. Leave your name, call letters in the radio station, and the city you're calling from, and then ask that question. Make that comment, and maybe you can get on national radio. Good day.